Good afternoon, everybody. And while you're entering the webinar, I might just say a few words of introduction both to myself and to iMOVE. So I'm Ian Christensen. I'm the Managing Director of iMOVE. And as I think most of you know, iMOVE is a cooperative research centre directed to working on problems and opportunities in the transport area. Of course, one of the big problems and opportunities that transport now faces is the challenge to decarbonise its operations. And as some of you will know, the different segments of the transport sector are finding that some of them are finding it easy, but some of them are finding it particularly difficult. So as the transport sector comes under pressure to decarbonise, there's a strong focus emerging on what are the practical ways in which this can be done. And of course, the most pragmatic path to decarbonisation at this time is the transition to battery electric vehicles. But refueling a battery electric vehicle is a rather different proposition from squeezing the nozzle at a petrol or diesel bowser. You and I can cope with this difference when we charge our electric car, but the differences cause problems when there's a whole fleet of vehicles that have to be recharged. And of course, this is the challenge that bus operators face. The many pilots and trials of battery electric buses show that the electric buses work and they actually deliver a good journey experience to the passengers. But to the bus operators, they pose big challenges. It's difficult to get all the buses sufficiently charged that they can complete their routes. And this challenge is further complicated by inadequate supplies of power to the bus depots. And a further complication is the variation in the price of electricity over the 24-hour cycle. It's cheap in the middle of the day when we've got lots of solar, and it's expensive during the evening peak. So I see a fair few complications and a fair few challenges. But the good news is that my colleagues who know about electricity supply actually see opportunities. They see opportunities to, by careful choice of the time and manner of charging, they see ways to reduce the total cost of the energy for the bus fleet quite substantially. But that's not my specialty. So we need to introduce somebody who knows a lot more about that subject than I do. And so I bring you James Seymour, who's the CEO of C4Net. Welcome, James. Can you share with us the opportunity that charging electric bus fleets might give us?
Yeah, thanks so much, Ian. And it's been fantastic to partner with iMOVE and RMIT on this research. That intersection of the energy industry and the transport industry, we don't know enough about each other, right? And we're going to be joined together at the hip going forward. So I'm really big fan of research in this area, and I commend the projects that iMOVE have done so well on. As we move forward, there are opportunities with electric vehicle charging, largely because it presents a flexible option within the electricity system. Now, from a transport point of view, we're always going to solve for having our buses ready to go and deliver the transport challenge that is there for them. And then it becomes, how do we charge in order to facilitate that? And that then there's some distinct charges on there. There's the initial connection challenge to the grid, because we now need a rather big pipe into these depots. We have the individual charging of each bus and how they are staggered and how there's a capital cost, operating cost trade-off that sits there. And then there's, of course, the variable price of electricity, both from the amount that you're using and the coincidental use of it, the peak use of it, and how that can impact bus operators. The good news, though, is that with the challenge of managing that, you've actually got more variables now And that means actually opportunities to win in there as well and lower the overall energy cost for the fleets. And that's really important. From a bigger picture, C4Net's looking at the overall system needs as we electrify transport, as we electrify our sector. And that's what we're doing under our enhanced system planning project. And I'd encourage anyone to have a look at our website on that project. One of the big levers in there is that if you can harness the flexibility that exists within the distribution system, you can significantly lower the overall cost of energy within that system. That flows through to consumers. And from a bus operator point of view, or a large transport fleet operator, that means that they can participate in value creation. And of course, that leads to value capture opportunities as well. There's one thing about trying to get the energy there. There's another around then optimizing within there. And that's where I really like this research and how Ali's looked at it. So I'll actually pass over now to Dr. Murati to take us through this amazing, the culmination of so much research. Ali, over to you.
Yeah, thank you. Thanks, James and Ian. Thank you very much. First I introduce myself. My name is Ali. I am a senior research fellow at the School of Engineering at RMIT University. And today I would like to share the outcomes of one of the projects that we did with iMOVE in collaboration with C4Net. The project is about spatiotemporal analysis of the charging requirement of Victoria's electric bus fleet. This is the project that we did in RMIT EV Living Lab. And just an introduction about the lab. This is the laboratory that we have recently established at the RMIT School of Engineering, Department of Electrical and Electronics Engineering. With the support of Victorian government, $5.2 million investment. Here in this lab, we can do almost any study in terms of integration of electric vehicles into the grid. And when I say electric vehicle, electric buses are also included. And from the larger scale, from the smaller scale, let's say, studies into the larger scale over the whole grid, we have facilities here to do the test. The lab is commissioned, and we are now using the equipment to do our test. And as a part of this laboratory, we are going beyond just technical electrical analysis, because we believe that electrification is not just a technical problem, it's a techno-economic and social problem. And we have started doing different techno-economic analysis. We have published 2 recent white papers explaining recent results of our research to the public. And if you are interested, you can go through the link to see what we have done. And we are really keen to hear from you any feedback. Focusing on the project started in January 2023, and the duration was 2 years actually. And the objective was that we know that ZEB trial has been run in Victoria, and there are a lot of experience and data collected from that trial. So we wanted to use that data to first understand how would be the charging requirement, electricity requirement for charging of electric buses when they go through the routes in the metropolitan Melbourne. And based on that, we wanted to go to the second objective, which is, I think, the most important one. How to do daytime charging for these buses if we go beyond depot charging, because we know that depot charging will be expensive when the electrification becomes 100%. And we know that daytime charging would be clean and most probably cheaper. So if we want to use daytime charging, where should we install the charging stations, and how much would be the size of that? This is the second question that we were looking for. In terms of data set, we went through the GTFS data set that is available publicly for everyone. Temperature data from the Bureau of Meteorology was also available. But data specifically for this project, we actually thank Latrobe Valley Bus Lines who shared this data set with us. The data set is data that is collected by Volvo Connect, the system which is implemented already in Volvo electric buses. And this data is a very high resolution data in terms of minutes, let's say. And it collects and records all activities in terms of voltages, in terms of driving behavior, in terms of total driving time and distance, number of bus stops, even if the the door opens, door closed. Most of the bus operators are familiar with this data set. We were lucky to have the data set with this high resolution from them, and it was very helpful for that. And another data set that we had was the data set for depot charging. It was also very helpful, showing that how much electricity they use and how frequent buses do charging activities. So with this data set, the idea was to first analyze what we can achieve from this data. And what outcomes we see is that first, with the ZEB trial data that we have, the average energy consumption of buses was between 1 and 1.5 kilowatt hour per kilometer. This figure on the right side shows the amount of energy consumption at different speeds. And we understand that when bus speed is less than 10 kilometer, or probably buses are experiencing frequent start and stop kind of operation, we see significant large consumption in those buses. But when the buses start running with the speed higher than 10 kilometers, the energy consumption comes between 1 and 1.5 kilowatt hour per kilometer. And also, we understand that the most energy consumption happens during evening time, between, let's say, 2 p.m. and 6 p.m., which is understandable, probably due to traffic that is happening. So, something which was actually interesting and supporting what we have in the literature. Literature always says that regenerative braking of buses or electric vehicles can restore about 30% of consumed energy to the battery. And here in this graph, this amber color shows the regenerative energy compared to the whole column, which shows the total energy consumption. We can see that it is almost 1/3, about 30%. So it proves that having regenerative braking can save about 30% of energy consumed by buses during travel. So after this data analysis, we went through the objective, which was actually extracting a model for the energy consumption of buses. And the most important thing is to identify the important features that we need to consider. There were several features that, let's say, addressed in the literature, from distance, speed, time, whether it's, let's say, peak time or, let's say, non-peak time, air conditioning, if we're working or not, route gradient, let's say the slope of the roads. And there were a couple of other parameters that we understand that during the analysis that they are not much important than the others, although they are still important. But we understood that most of the, let's say, energy consumption varies due to these parameters like speed and route gradient. And we went through different, let's say, machine learning algorithms that we have as a methodology, neural networks, support vector machines, and then at the end, we actually introduced a new methodology based on the ensemble of these methods in order to make sure that the accuracy is maximum. And we implemented these methodologies. We compared them together to see which one works better. And finally, we verified that this is this machine learning model based on the ensemble technique that we proposed can estimate the energy consumption more accurately than the others. And this was the time that, okay, this is a good one. Let's implement a tool for estimating the bus energy consumption. We went through developing a tool. I want to show this tool to you online. I need to, I think, reshare it. Okay, this is the tool that we have developed. This is an online tool. The link to that will be shared with participants after this meeting. The idea of this tool was to estimate the energy consumption of buses for each route. So we have here a table that operators can complete it. We have bus route numbers. This is the list of route numbers that we have based on the GTFS data. It is not all of them. It doesn't contain all of them because the data set that we have was not rich enough to cover all routes. But those routes we can cover. They are all here. We can choose the bus route that you want to see the energy estimate. You can choose the whether it's cold or hot or let's say pleasant. These words have a meaning of range of temperature. That should be added probably. And based on the weekdays or weekends, let's say on weekdays and the buses that we have only one type of bus here because we understand that the type of bus is also important in the energy consumption. Mainly the weight of bus is something very important. And the state of charge of the battery when it starts the route, you can actually enter it here. And then once you press the energy consumption, this data will be transferred to the machine learning model that we have already trained based on the data. And it comes to you with, let's say, just one map to show the start and end of the route, as well as some information about the energy consumption and the gradient and those stuff. And here it shows that, for example, for this specific route that I've chosen between Box Hill and Mitcham stations, the total distance is about 10 kilometers, and the average speed that is, let's say, recorded is 25, and the total energy consumption is about 10 kilowatt hours, so one kilowatt hour per kilometer almost. And there are also other information, but the most significant part of these are these two. So the link to this tool will be available after this meeting. As I said, this is the tool that we just initiated based on the data set that we have. Any richer data set will help us to make it to improve its accuracy. And if you see any opportunity to share, let's say, more data set with us, that would be something great that will help us in establishing this tool. I'm now back to my presentation. So, sorry, I need to reshare it, I think. Yeah. Okay, this was the first, let's say, work package of this project that finished with the establishing that tool. As I mentioned, it was just an initial try. The second part of the project, which was most important part, was the optimal size and location of charging station. How we can minimize the number of charging stations let's say, around metropolitan Melbourne, while the service based on the GTFS files are served. So the problem is very big. The size of that is large. You can see that we have, let's say, more than 1,800 buses in metropolitan working every day. So having, let's say, addressing this problem around whole metropolitan has a, let's say, computational complexity. In order to reduce it, we had, let's say, a couple of assumptions. The first one was that, okay, we assumed that the schedule of electrified buses will be exactly the same as the ICE-based one based on the GTFS files that we had. So if the bus is electrified, it still follows the same schedule. And the second one was that we limited our charging points to interchanges and terminals. So we did not consider, let's say, en route charging, let's say in the bus stops on the route, because we see that most of the bus stop they don't have opportunity for installing charging stations, and sometimes buses do not stop actually there because there is no passenger for that. So we limited our study into interchanges and terminals, and the methodology that we used was a mathematical optimization problem. This is a really innovative, let's say, methodology that we developed for this one. And it is based on, let's say, a graph theoretical model. I don't want to go through the, let's say, details of that because I know that it's very complicated, but what we have considered is that a bus leaves depot, for example, in the morning and comes to the, let's say, first station, station 1. And from that, it starts to go through a couple of routes based on the schedule. And during those routes, when the, let's say, state of charge of the battery reaches 20%, let's say, or 30% or 40%, is the flexibility that we can set. At that time, bus needs to go to charger, get charged, and then come back and then start continuing the trip until the night time that it goes to depot, let's say, again, goes to depot from one of the stations. So this is the, let's say, assumption that we have considered. Definitely the buses who are getting charged during, let's say, after a trip, they need to follow the schedule, so they have a very limited time to get charged. And during that time, they will have, let's say, limited amount of top-up charging during that time. So this will specify the size of chargers that we require and also the location of chargers that should be installed. And also we try to reduce the size of the problem. This left figure shows the number of the location, let's say, of terminals and let's say end stations in metropolitan Melbourne, and we try to consolidate those who are very close to each other, and we consider that, okay, there are terminals which are close to each other, but if we want to install a charging station that serve all of them, we need to consolidate all of them to just to reduce the size of the problem that we are solving. So based on this, we designed the optimization problem. We actually solved it using very high performance computers. And what we achieved at the end is, you see, this is metropolitan Melbourne. We have a couple of points in green and a couple of points in blue. And these green points are, let's say, the first candidates that preferably we install charging stations in them because of the size of charging station that we require. The largest size will be here. For example, the major charging demand will happen in Frankston Station, Chelsea Station, Sunshine, Melbourne Airport, and all to Craigieburn Station. And these green charging stations will serve more number of buses during the day, so they need, let's say, more charging piles. So, for example, here, it's the information that is here mentioned is that the number of buses that we require to serve this network is 1849. So one important thing is that if we want to do the charging during daytime, most probably the number of buses that we have now is not enough, so we need to consider the number of buses and as one of the optimization parameters that we need to solve. So we have electrical stations, 51 electrical stations, and the largest station have, let's say, 5 plugs for charging. And there are other information here that's relevant to this size and location of these chargers. One important thing here is that the framework that we develop is flexible to consider that, to specify when the bus needs to go to charge. Is it when the state of charge of the battery reaches 20% or 30% or 40% and so on? And you know the importance of that, because when we increase this number, let's say a state of charge before going to charging, that means we are increasing the amount of electricity, amount of charging that we are doing during daytime. And that means increasing clean charging and increasing most probably cheap charging. So it will help bus operators mainly in order to reduce the operational costs when they are operating, let's say, high penetration of electric buses. Yeah, this was the second, let's say, outcome of this project. The result of the first work package transferred to the second work package in order to have an estimate of the energy consumption. And finally, we identified the optimal locations of chargers and the size of them. But what next? What we think we see that, let's say, we see as the opportunity. As we understand from discussing with the bus operators, we are now almost confident that electric buses can do the job in terms of, let's say, moving people. And the ZEB trial shows that, okay, they work almost well. It seems that there are opportunities, economic opportunities, to make this transition, this electrification, economically viable, because we know that it's expensive. Buses, electrification of, let's say, depots, and the other things are very expensive. So how we can make it economically viable? So this is an example that we have internationally in the Glasgow, UK, and this is a bus depot for over 150 buses. I mean, 150 buses can be charged at one time. So we have, let's say, 150 almost high power chargers here. And the good thing with this, the location of this charging station is that it's located in an industrial area. So during the daytime, when buses are out to service, these chargers are free. And let's say companies or industries who are here can come and use them and definitely pay for the electricity that they use to charge. So this is source of revenue for this bus operator, which make it viable, and that send a message that probably best locations for depot electrification is not depots who are far from industrial areas. So if there is an opportunity to share the charging with the others, with the local community, that would be probably a source of revenue. But this economic aspects of this problem, of this electrification, goes beyond that. We need really a business model specifically for depot charging. And the most important thing is the number and size of the chargers, because at the moment we are thinking about, let's say, having one charger per bus. And probably we can think about more optimal solutions, reducing the number of chargers in each depot. And we know that as the number of chargers goes high, let's say the maintenance of them becomes problematic. the update of the system becomes difficult because the technology is really changing, and who knows what will happen for these electric buses in 10 years. What will be the technology and how we can serve them. So the number and size of the buses of the charging stations, sorry, in the depots should be really optimized, and this is something that we need to consider in the business model. And also about the charging plan, how we can integrate the charging time into the existing bus schedule, considering that, okay, we want to have cheap charging, we want to have clean charging. So how we can change the schedules in order to have these two together. And one of the let's say buzzwords that everybody talks about when goes to electrification is V2G. And we know that V2G requires, let's say, significant facilities and infrastructure to be implemented. But at the time that is doable, this V2G can bring a source of revenue for depots. Because suppose that you have 100 buses stop there and let's say they have 100 kilowatt hour electricity left in each battery. So that's a very good source of energy if we want to support the electricity grid during even peak evening time and gain money. So why not? This is another opportunity for making it economically viable. And also about the dynamic bus allocation, which is a problem, let's say, very interesting problem in the transportation side. When it comes to the electrification, electric buses, we need to consider electric constraints, let's say, integrate electric constraints to that. So addressing the dynamic bus allocation problem, considering the limitations that we have from the electric buses, is something that needs a lot of research at this stage. And more research should be done local, because the pattern that we use electric buses, or generally buses in, for example, in Victoria, is probably different than what people use in the UK or the other countries. So local studies require to finalize this. So if I want to wrap up, just my focus is now on the economic aspect of the transport electrification in the buses. And I see that there is a very important point that needs to be addressed if we want to facilitate this electrification. And by this slide, I think I will reach the end of my presentation. I tried to make it very short and concise. I hope I've done it. So I appreciate the participants if they have any questions or comment or discussion.
Thank you, Ali. James, since you've only got a short time with us, do you want to make some wrap-up comment?
Yeah, so Ali, great to look across. And I love that example of the UK there, where there was there's the massive infrastructure that needs to come in, but utilizing it over different applications. And I think that type of creative thinking is something that is not something that we think of instantly. And things like our bus depots are largely landlocked. You know, we're not going to be able to just move them to where the optimal point is type thing. So it's more around that thinking of how do we optimize within there and everything. What I recognize as well, there's quite, and I actually think I got this from the iMOVE conference, which was really interesting. But there was some great research out of the UK and Europe, which supported that little bit of charging along the way can make a big difference in the overall robustness and resilience of the fleet to take in the be opportunistic and charge up. but also to lower costs in there. Have we seen that applied in Australia yet, or is it just that we're just modelling it to the potential that could be there? Have we seen it anywhere around Australia yet?
I haven't seen any report at the moment because what I see is that in Victoria, the electrified depot that Ventura has in Ivanhoe, they have one,
That's a back to base.
Exactly.
Yeah, that's a back to base.
Yeah, and for New South Wales, we have the similar, let's say, strategy. So these are kind of, I don't want to say innovative, but the solutions that are focused on the economic aspects as well. At the moment, what we have done in Australia, we were trying to understand, okay, is it doable here, and how we can establish it? And now we are confident enough that, okay, it is doable. Now let's go and how we can make it economic. I think the next step that probably the bus operators will consider in Australia would be some innovative solutions like what we see in UK.
Yeah, okay. And certainly, like you raised the Ivanhoe depot, it's interesting for all just some of the challenges that come through.
Exactly.
Are in some ways pretty basic, right? So, we're talking about optimizing and all of that. Can I get the bollards in the right position? Can I, can I get the data from one device to another in a way that's readable and everything? These are some of the early teething problems that are sort of coming through. How do I understand my electricity bill? And hold on, why isn't it written in a way that I can understand it and move? These are some of the challenges that's there. But I think we forget the learned behavior around diesel purchasing strategies, fuel purchasing, hedging type things that are all there. This is just a new world that we move to with electricity, but it does come with opportunities. So that's really exciting. Ian, I think we've got some questions.
We do
there
have
from
some
the,
questions.
And
before I go to the ones that were in the Q&A section on the screen, I'm actually going to start with one that was sent to us even before the webinar started. And that's a question about the likely effectiveness of wireless charging. So the question is wireless charging for buses sufficiently efficient enough that it could support depot charging, or is it problematic? Wiley, did you look at wireless charging anywhere in your modeling?
Yeah, wireless charging is actually mainly used to reduce the time, let's say, to be used during opportunity charging or top-up charging, while we don't like the buses or electric vehicles to stop for a long time and get connected to something. So there are trials around the world implementing wireless charging in bus stations and bus stops. While, for example, the bus is stopped for 5 minutes, a top-up charging will happen during that. And but it is still under trial, and still not sure that is it better to have wireless charging in one stop to charge the bus when it is stopped, or it's better to invest in electrifying terminals and intersections and use that one to do the charging. This is still something that is under a trial and under research.
Thanks. So Daniel asks us, did the model factor in charge from in-depot charging either during the day, during the day in the off-peak or overnight? So I'm imagining that you did.
Yes, we assume that the bus is charged, let's say, from the depot and leave depot early in the morning. But all other charging during the operation will be done, let's say, in the city, let's say in the metropolitan, and then at night bus comes back to depot. So we can decide how much should be the charge of the state of charge of the battery when it comes back to depot. So if we increase it, for example, to 60%, that means we are pushing charging during daytime out of depot, and then bus comes back with 60% of energy into depot.
Thanks. And staying on the subject of in-depot charging, did you consider the installation of a depot battery that could absorb energy either from the grid or from rooftop solar in a way during the day, and then be used to charge the buses at depot at night? Does that work both operationally and financially?
Having a battery installed in depot, specifically for bus depots, it's a matter of question. There are a lot of research showing that it's not economically beneficial. The reason is that suppose that you have 1 megawatt battery in the depot. So 1 megawatt battery is only enough to charge 3 buses, not more. And having stored energy and charging just 3 buses in a depot of 100 buses, that means almost nothing. The only successful story that we see in the literature is that battery can support the operational, let's say, electricity of the depot during peak time, not for charging buses. If they have anything, for example, like workshop, like the other stuff that are consuming electricity, yes, they can. The battery can support that and can reduce the electricity costs significantly. But I haven't seen any, let's say, success story about charging buses through battery on depot.
So again, staying with depot charging, Christina is asking whether you modeled the constraint of charging only at the depot. So in a way, having no opportunity to charge en route or at another destination, then is it feasible to supply enough energy to the buses from just depot charging effectively overnight so that the bus has a fully load? Well, yes, the bus has enough charge to do the whole day or the whole day of operations until it returns to depot for its next pause.
Yeah. The reason that we go actually beyond depot charging, because depot charging is the simplest situation that we can consider. Why we need to go beyond that? Because suppose that you have a depot of 100 buses and each bus needs, let's say, 200 kilowatt hour of energy in order to get fully charged. So that means 20 megawatt hour of energy that you need to, let's say, absorb from the grid during evening time, let's say from 6 p.m. to, during night time, from 6 p.m. to 5 p.m. next morning. Considering that from 6 p.m. to 10 p.m. 9 p.m. is kind of, let's say, peak hours. And most probably the electricity distributor will not let you absorb, let's say, electricity a lot. That means focusing only on depot charging is probably operationally impossible when we go to 100% electrification. That's why people are focusing towards off-depot charging. Additionally, the cost of charging is important. So as I said, daytime charging would be cheaper, and that will help the electricity grid, because most of the time during daytime we have negative electricity prices in the electricity market. So if we have a stable consumer there, probably good deals of electricity would be available for them.
So again, still staying with chargers, can you share with the webinar participants the specifications of the chargers that you used in your model? So how big and at what cost?
Yeah. The charger size that we considered here is a 200 kilowatt charger. So this is a normal charger that we can consider for bus depots. We can go beyond that. We have chargers with more capacity. And this is the only, let's say, limitations that we considered there. About the type, we didn't have any constraints.
Would it make a difference if you went from plug-in charging to pantograph charging?
Again, pantograph charging and wireless charging are the other opportunities. Pantograph charging is mainly used for where buses can stop for a limited time, let's say. So for depot charging, in which buses are parked during night, probably pantograph charging is not a good solution. We can still stick to these plug-in chargers and leave pantograph and also wireless charging for short time top-up charging during daytime.
So you mentioned just before when we were talking about depot-only charging and the sort of the lack of operational feasibility and the suboptimal pricing that would prevail. There are two questions now in the Q&A asking about the size of the opportunity for the bus fleet or the bus operator to participate in the energy market by using the fleet's battery capacity to absorb as much energy when prices are in the middle of the day when prices are zero.
Yeah.
Never mind the operational difficulties of that, but nonetheless to sort of reconfigure the problem to being, well, let's treat the bus fleet as a mobile battery that just happens to also carry passengers around the suburbs. Did you look at it, in a way from this sort of alternative perspective?
It is something that we are now doing research on. We have started just research on it, and we understand that charging the fleet and let's say battery which is installed in depot during daytime and making it ready to contribute in the electricity market during peak evening time, let's say 7 to 9 p.m. or whatever, is something really doable for bus depots, because as I mentioned, the capacity of capacity of energy stored in the batteries of buses is significant, and they can definitely contribute in the electricity market. We should know that during that time, charging shouldn't be happened in depot, so we need to consider that if we exclude that time from charging, do we have enough time to get buses fully charged during the nighttime or not? But this is another problem, another optimization problem, and this contribution to the grid is definitely doable. We have received good research results in the literature showing that this is very cost-saving for bus operators, and this is something that we have started working on, as I mentioned.
If I can, I just might add to that, and some observations from the trials that we've seen go ahead. The sizing of the batteries in the buses tends to be pretty conservative. In other words, we're generally carrying it because it is such a dire situation. If we were to run out of electricity, just as if we were to run out of diesel mid-route or something, it impacts the operations. The design is such that there is a lot of redundancy in there. That's great. That covers all the sort of aspects that are there. And we saw that the state of charge was rarely dropping below 50%. 50%. Well in advance. All of that other stuff there is then the opportunity. And you can do that completely on your terms. In other words, that's because you're only doing it by exception. How much you charge up or how much you potentially discharge is in the bus operators' opportunity. They can take advantage in future of that redundancy that sits there to be quite dynamic to the energy market, and that's something that you can't do. We don't pump diesel back out into the system or anything like that just because prices have changed or anything like that. But that's arguably the what you can do in the future. And a question there from Christina around the duck curve and everything. That's exactly the type of thing that you can respond to, and likewise with a peak. So it can be quite situational.
Exactly.
So I like the idea of using the bus fleet as a sort of a way to absorb midday solar solar renewables. But I'm thinking, if I'm a bus fleet operator, how am I going to connect my buses to the plug or to the grid to absorb that energy in the middle of the day when I'm really expecting them to be carrying passengers around the routes? So my question kind of goes to, so would it be necessary to, let's say, double the size of the bus fleet in order to be able to simultaneously deliver the passenger service on the one hand and participate in the energy market, particularly with the drawdown of energy into the buses in the middle of the day? So there's kind of, it sounds like a free lunch, but I suspect there's no free lunch here.
No, I think what we see from the literature doesn't show that you need to double the size of the bus fleet, let's say. An increase between 10% to 20% is reported, but it definitely depends on the size of the battery. As James mentioned, size of the battery of buses are very important. And also the way that we operate buses is also important. Definitely, the European style is different than what we have in Australia. So what I can say, it would be something between 10% and 20% increase in the size, but based on the literature, but it requires, let's say, specific studies.
And certainly in terms of doubling or anything like that, the capital cost isn't going to justify that.
That's true.
Energy is a pretty skinny game that's there. What it's more saying is that even when you have solved for your operational needs, chances are you still have some flexibility around the edges from the redundancy that you have to carry anyhow. And now it just becomes a multivariant problem where you're solving not just for the operating needs, but you can start factoring in those energy needs or opportunities as well. It's pretty rare that the depot is completely empty. You've usually got some redundancy there. Well, that's an asset that you can actually utilize now rather than sitting there idle. It is an asset that can sit there idle but be connected to the grid and actually be changing the economics for you. So that's more the type of thinking there. And look, that goes to a couple of Jason's question around can it export? Yes, that's the V2G that Ali was talking about. And then Cheryl's question around the interactions between, is it that different charging a bus compared to no, they're largely that's that part of that opportunity to optimize there across fleets and everything. And it also goes to your question before around a battery stored at the depot, because it was thought of that maybe that's needed in order to provide the redundancy, that's there. In general, charging a battery doesn't make sense. But in the very, very rare circumstance where there is a locational blackout or restriction, you drive to the next depot. Or you drive to the next trucking fleet, because they are interchangeable. There is a degree there. So there'll be redundancy there.
So, James, that's an interesting answer. When you think about Cheryl's question about the interaction between the bus fleet charging and truck fleet charging, and Ali, I recall your slide, or I think it was the model, where you identified the locations where you've got aggregations of buses needing charging, and that makes for a suitable location for a charging hub for buses. But I think Cheryl's question takes us to an even bigger opportunity, which would be, so where do we have a co-location or coincidence of demand for bus charging and demand for truck charging that could justify the establishment of a really quite sizable charging operation and commercial opportunity.
Yeah, I want to expand it.
A way to build trucking into this this model.
I want to expand it and ask a question that, okay, now a lot of councils, city councils are getting electrified. Where should they charge their asset? Buses are getting electrified. Emergencies are getting electrified. If we consider electrification as a project of the whole city, we need to consider charging infrastructure as an infrastructure for the whole city. That means everybody should be able to use that. I cannot say that this charging station I installed it just for buses, while, for example, council fleet doesn't have charging stations. They should be able to use it as well. So this is a very strategic planning that we need to consider when we go for electrification. It doesn't enough to say that, okay, a lot of, let's say, third-party companies will come and install chargers for us, that will solve our problem. No, we have a lot of fleet that need a specific requirement for charging. For example, buses, they have a specific commitment for mobility. City councils, they have a specific commitment for services, and we need to decide strategically for them. So the question is a very valid question. And I know that this is kind of, let's say, management problem still in the, all around the world, how we can manage it, because up to now, bus operators will working only with the Department of Transport, energy sector working with only, for example, with iMOVE, but we need to come together anyway to solve this problem.
So as a kind of probably the last point, but taking that point from another direction, what would you recommend to bus operators what do they do next? How do they benefit from the research that you've just done?
I think definitely we are waiting for feedback from the bus operators to see what sort of problems they have. But from the understanding that we have from talking with the Department of Transport and Planning, we understand that the economic part of the problem of this electrification is very important for them, for the bus operators at this stage. We see a lot of opportunities to reduce the operational cost of the of electrification, and this definitely is not an easy transition. It would be an expensive transition to electrification. So if we want to make it economically viable, we need to consider short-term, mid-term, and long-term plans. I mean, from the bus operator perspective, in order to make it doable. And in the short term, I think operators need to focus more on depot charging, and make it more optimal, reduce the cost, specifically during peak times, and then expand it to the daytime charging and the, let's say, citywide charging and those stuff.
And remembering that all of that cost side is completely balanced against the reduction in diesel
That's it.
purchase. So.
Yeah.
So we've come to the end of time. Please join me in thanking James Seymour and especially Dr. Ali for a really interesting presentation.
Thank you.
Thank you very much. And I would just like also call out thanks to Christina in the audience for her very well-informed and insightful questions and responses to some of the issues. Christina, I think it would be, you obviously know about bus operations, and maybe it would be a good idea if you made direct contact with Ali.
Definitely.
That would be wonderful. Thank you all very much. The report from Ali's research will be emailed, or a link to the report will be emailed to all the participants in the webinar. And I really thank you for your time, attendance, and participation. Thanks very much.
Thank you.